Multimodal LM roundup, Unified I/O2, inputs and outputs, Gemini, LLaVA-RLHF, and RLHF questions was published on January 10th, 2024, a sampling of recent happenings in the multimodal space. Be sure to expect more this year. Everyone knows that multimodal models are going to be a big theme for the year, but I have yet to read a compelling argument as to why. To me, it's based on grand goals for what AI should be able to do and complement the core functions of our information processing capabilities. What multimodal inputs to models do is take us one step closer to letting large language models, LLMs, see what we see. Text was the primary form of visual information for a few centuries, but with TikTok and YouTube, our society is increasingly visual. There was a small phase where audio only seemed like the next modality, but it remains niche relative to video, and text can normally be used instead of audio. To this end, image inputs can unlock a way richer set of training data and applications. On the other side of things is what multimodal outputs allow. The most impressive thing about the Gemini announcement to me is that it can natively generate images. Outputs are about creative acts, which are certainly complementary to information processing, but can be understood in their own way. With this separation of generation and information processing, the various parts of building multimodal models can mirror the encoder-decoder architecture of earlier LLMs. Those used today are almost entirely decoder-only. This multimodal worldview is definitely a work in progress. So let me know if there's a resource you like on the topic. The notation for multimodal large language models, MLLMs, is also a work in progress. Some people refer to them as that MLLM, but also the terminology visual language model, VLM, is used widely. It's easy to see that visual is a subset of multimodal, but we need much clearer terminology when we want to differentiate between models like OpenAI's GPT-4V and Google's Gemini. OpenAI's models only read image inputs, while Google's also outputs images. That is likely a huge difference in architecture and training methods. This post roughly follows the normal training pipeline, starting with a paper about pre-training, moving through data collection, and finishing with LLaVA-RLHF and open questions. Unified I/O2, scaling multi-input, multi-output model pre-training. This recent paper and model release from the Allen Institute on Unified I/O2 caught my eye because it was the most relevant work to Gemini in training a model for multi-output operation. Unified I/O2 is, in short, the first autoregressive multimodal model that is capable of understanding and generating images, text, audio, and action. To unify different modalities, we tokenize inputs and outputs images, text, audio, action, boxes, etc. into a shared semantic space, and then process them with a single encoder-decoder transformer model. A summary of the architecture is shown below. The core of multimodal models is figuring out how to share the tokenization space across a variety of signals, both for inference and training. See figure. You can compare this system diagram to another popular multimodal language model, Flamingo, from DeepMind. See figure. When you compare these to Gemini, a keyword is missing from Unified I/O compared to Gemini, which is interleaved. Google says that Gemini can output responses with interleaved images and text. I want to know how stable these behaviors are and how much work it takes to get the model to do both nicely. At a minimum, it seems like a substantial change in how pre-training data is structured. Normally, pre-training data processing will strip all images from sources, but for Gemini, they may need to leave them in line. Additionally, we don't know if adding this output ability improved the language-alone capabilities, or if Google trapped themselves on a specific development pathway and got stuck with it. We'll learn more soon. See figure. My primary questions for the authors and paper fell into two categories. First, I wanted to know what problems emerge when you add more modalities in pre-training. Second, I wanted to know if they tried any instruction tuning or RLHF. The pre-training architecture is built on UL2 from Google. The authors shared some of the substantial efforts it took to get off the ground in the paper, and in a talk I got to watch internal to AI2. As a summary, they stated that model is not stable when use pure NLP LLM training receipts. QK normalization, apply layer norm before QK attention. Scaled cosine, attention in perceiver. Avoid unbound value happens there. More likely to have numerical issue. F32 attention logit instead of BF16. Out of factor is better than Atom W in our optimization setting. Carefully curated mixture ratio that consider the modality distribution, data quality, and size. 2D rotary encoding. Auto-regressive with dynamic masking. In the interest of brevity, I'm continuing, but you know to look at the paper for more. They also shared the tooling they needed to do this. Dynamic packing. Efficient packing mechanism that can reduce the padding of unused modality tokens leads to 4x improvements throughputs. CQIO, super efficient data pipeline that easily mix arbitrary multimodal dataset. T5X, model paralleled implementation that can scale up the model. Ultimately, they tried using the T5 model as a starting point because that was a code base that worked for V1 of the model, but that didn't work out of the box. They needed to do a lot of sampling around how much data was used for each subdomain. There's currently vastly more text data available than domains like key point estimation. This sampling problem is important to getting a stable loss. The language corpus they used before any subtle sampling changes was designed to match that of the MPT model. The authors did use a sampling of text and multimodal instruction tuning datasets, which gives the usual bump. I'll discuss more on multimodal fine-tuning in the section on LLaVA-RLHF later. See figure. Evaluating models like this takes a large effort. In short, the text-image capabilities are pretty comparable to LLaVA models. On language-only tasks, this model is closer to the 3 billion parameter text models. More information for Unified IO2 can be found on Twitter, and a good sampling of the results via example audio and sequences is on the project website. The https github.com, LNA, Unified, IO2, and checkpoints are available. In the future, reproducing this type of work with decoder-only architectures would be compelling. This will take a lot of engineering effort, and the authors mentioned that parameter count would likely matter more at this point. At another time, I'd like to go back and revisit some of Meta's work in this area with CM3 on Meta's blog post, and paper would be the starting point for that. Collecting preference data for images. Collecting preference data over text alone is much harder than images. For example, Midjourney has been showing users 4 outputs for quite a while and asking them to select a specific image to upsample or vary. Whichever image you choose is the preference label. See figure. This behavior has been copied across a ton of model suppliers like Ideogram or DAL. It's likely due to saving compute that ChatGPT's DAL integration doesn't have this. A more interesting variant is a dataset I see being made by the hot company TLDraw. The thing is, right now, they're feeding it all into OpenAI's API, so hopefully they turned off the setting train on my data, which is on by default. Essentially, TLDraw works by passing in images with a special prompt to GPT-4v to get functioning web code out. The interesting part is how you can apply comments directly on the canvas and regenerate the element. In the figure below, the founder Steve Ruiz shows from Latent Space. What happens if you just add a short nudge in the form of written text to GPT-4v? It'll often fix the problem. See figure. From this, there's a preference pair for GPT-4v based on the original prompt, and then the first generated code would be the rejected sample, with the minor follow-up being the chosen sample. These sorts of real-world usage in multimodal RLHF will be the most valuable. We'll see that most of the academically available visual RLHF data will be limited to data augmentation to start, which I expect to have less compelling areas of application. LLaVA-RLHF. The first experiments in multimodal RLHF fine-tuning. Large Language and Vision Assistant, LLaVA, was one of the most popular papers at NeurIPs, with more details shared in the V1.5 report. The models, of which there is a V1 and a V1.5 at both 7 billion and 13 billion parameters, represent some of the first easy TAUS and benchmark strong open visual language models, VLM. This wasn't surprising to me, as it seemed like more of the same exciting news from the new pace of ML developments. What caught both my eyes and the eyes of many in my network was the LLaVA-RLHF paper, which was seemingly the first open, substantial RLHF tune for a VLM. At least it was the first one, the breakthrough. The work involves two primary axes, a new factually augmented RLHF technique, FACT-RLHF, and a new synthetic dataset generated with GPT-4V. The system diagram is quite good, which at first looks like a normal three-stage RLHF process figure, but is really about the signal flow of correcting errors in multimodal instruction data. See figure. The first sentence of their abstract points the work directly at investigating my most pressing questions about multimodal RLHF. How do we cross modalities during instruction tuning and RLHF? It reads, large multimodal models, LMM, are built across modalities, and the misalignment between two modalities can result in hallucination, generating textual outputs that are not grounded by the multimodal information in context. To solve this, the paper does most of its work around generating data that relies on both modalities and learning how to evaluate it. Regarding data, the authors create high-quality instruct data. We convert VQA V2, A3K, and ROKVQA 16K into a multi-round QA task, and Flickr 30K, 23K into a spotting captioning task, and train the LLaVA-SFT plus models based on the new mixture of data, including LLaVA Instruct 90K, randomly sampled from LLaVA Instruct 150K. For better linking of images and text during training, the authors propose factually augmented RLHF. We introduce a novel algorithm named factually augmented RLHF, FACT-RLHF, which calibrates the reward signals by augmenting them with additional information such as image captions or ground truth multi-choice option. The reward model is trained on 10K hallucination-aware human preference data. The other contribution of the paper is MMHalBench, a dataset with 96 image question pairs ranging in 8 question categories and 12 object topics from open images. This feels like the early days of finding something like MTBench and Alpaca Evil for multimodal inputs. They show that using their RLHF technique gives a moderate bump on benchmark scores. I'm not particularly versed in various VLM benchmarks, so it's not time for me to add commentary on how strong the models are relative to GPT-4V beyond the obvious fact that there's a long way to go. A good summary of at least the peer models is in Table 4 of the paper. MMBench defines 20 abilities of multimodal models. See figure. As someone who was at Hugging Face for the IDAFIX training, I'm impressed to see how fast it was surpassed. That's how it goes this year. If you can't keep releasing new iterations of your model, you fall behind. Multimodal RLHF questions, ideas, and resources. My core question around multimodal RLHF is how to merge work streams and goals. How do we balance the data that is language only with the need to be always training with images, or the model will overfit to text? What percentage of image data is needed in the pre-training versus fine-tuning corpus? How are people even going to use chat VLMs? Would our existing data sets like ultra feedback even apply to the new use case? How much harder in terms of accuracy, diversity, and cost will it be to generate multimodal preference and instruction datasets? We've seen how extensively GPT-4 is used for open LLMs that are text-only. As far as I know, GPT-4V is way more expensive than text-only, and it comes with a new set of safety filters to get used to. In short, we'll have the same GPT-4V datasets as ultra feedback, but we're far from understanding why these work. We need to study them with text-only first. A related area in my mind is multi-objective RLHF. From the Gemini paper, we use multi-objective optimization with a weighted sum of reward scores from helpfulness, factuality, and safety to train a multi-headed reward model. Does progress with methods like this make it easier to translate to multimodality, or does this only apply when outputting images? Some more resources I found in this area are a 2022 DeepMind paper, Improving Multimodal Interactive Agents with Reinforcement Learning from Human Feedback, a roundup from Davis, summarizes papers on multimodal RLHF and chain of thought focus on diffusion. The Instructable paper from earlier in 2023, a systems paper on multimodal generation from Meta that may have hints, Silky preference distillation for large visual language models, RLHFV, towards trustworthy MLLMs via behavior alignment from fine-grained correctional human feedback, which releases the dataset, and another recent paper on scaling VLMs. I'm most excited to see how creative people figure out how to make synthetic data work here. I'm guessing people will try and save money and use things other than GPT-4V, such as multiple models in one synthetic data system. Thank you for listening and have a great day.